Hello everyone, welcome to the course Basics of Materials Engineering. In today's lecture, we'll be talking about thermal processing and heat treatment of steels. This course is offered by Professor Ratna Kumar from Department of Mechanical Engineering, IIT Madras. I'm your TA Alka Jangit from IIT Kanpur. Firstly, we'll be going through some sample assignment questions, then we'll be going through some lecture notes. So, your first question is, radius of the new nuclei formed during heterogeneous nucleation depends on. Your options are delta T, which is undercooling, S theta, which is a function of the wetting angle, A, surface area of your parent particle, or V, volume of your parent particle. So answer will be undercooling. So as in case of homogeneous nucleation, in heterogeneous nucleation also, your nucleation formation depends on your undercooling. So the radius of the new nuclei in the case of heterogeneous nucleation is inversely proportional to the delta T. So higher the undercooling, lower will be your critical radius required for your nuclei. So this is the same when you take homogeneous nucleation, but there is much lesser degree of supercooling needed for heterogeneous nucleation because there is all a surface energy already present in case of heterogeneous nucleation. Second question is, calculate the value of critical free energy if the value of delta Gs minus delta Gv is given as 22 upon 7 times half, where your gamma presents the surface free energy. Your options are 16 by 7 gamma cube, 76 by 3 gamma cube, or 16 by 3 gamma cube, or 3 by 16 gamma cube. So your answer will be 16 by 3. So for this explanation, you should know the equation for the your total free energy. So when we differentiate the equation related to the total free energy with respect to free energy, we end up with the equation 16 by 3 pi gamma cube divided by delta Gs minus delta Gv square. So here delta Gs minus delta Gv square is pi root cube, square root of pi. So it will be square and pi will get cancelled, and 16 by 3 gamma cube will be answer. Third question is, how does temperature affect nucleation? So your options are, nucleation is directly proportional to temperature, nucleation is indirectly proportional to temperature, or nucleation and temperature are always at equilibrium, and nucleation and temperature does not depend on each other. So nucleation is indirectly proportional to temperature. So in this case, as we keep on, for nucleation you always require some supercooling. So for supercooling it will be your delta T. So delta T in case of delta Gv is your driving force for nucleation. So it is proportional to delta T. Your driving energy is proportional to supercooling. So, and in case of size of nucleus will be inversely proportional to your delta Gv. So the decrease in nucleation centers at high temperature interprets that a decrease in supersaturation would increase the critical size of nucleus and free energy of nucleus formation. And from this also you can say that your activation energy required for nucleation reduces when you take a temperature which is lower. For T2 which is lower than T1, you will be requiring less critical size of the nuclei So it will form a fine structure. Fourth question is, if the steel is suddenly cooled from 900 degrees Celsius,
Ma'am, your screen is not visible.
screen is not visible. Now, Sanjeet, is it visible? No, no, it's not visible. Sorry for the interruption. I lost internet. Now is it visible, Sanjeet?
Yeah, yes, ma'am, it's visible.
Okay. Okay, so in fourth question, please mute yourself. Oh, yeah, thank you. So for fourth question, if the steel is suddenly cooled from 900 degrees Celsius, here up above your A1 temperature, where above this there will be only austenite form. So after this, from 900 you're cooling up to 600 degrees Celsius, which will be here, around here, and held there for 100 seconds. So the resulting microstructure will be, your options are 100% coarse perlite, pro-eutectoid cementite plus fine perlite, and pro-eutectoid ferrite plus fine perlite, or pro-eutectoid ferrite and coarse perlite. So your answer will be 100% coarse perlite. And this is your cooling curve. So here first you are rapidly cooling up to 600 degrees Celsius, then you are isothermally holding it at 600 degrees Celsius. So after that you are cooling it further below after 100 seconds. So in 100 seconds you can see that your transformation will be almost complete. So there will be 100% coarse perlite formation. And these for these steps, so initially when you're suddenly cooling up to 600 degrees Celsius, your austenite here it is stable, and below eutectoid temperature it is metastable. So on holding it for 100 seconds, this metastable austenite will be transforming into 100% coarse perlite. Now similarly here you are cooling up to 500 degrees Celsius, which is below your nose temperature. Nose temperature is here, and below this there will be formation of bainite. So your question is, if the steel is suddenly cooled from 900 degrees Celsius down to 500 degrees Celsius and held for 100 seconds, followed by sudden cooling to room temperature, the resulting microstructure will be. Options are fine perlite, 100% vanite, 50% austenite plus 50% perlite, or 50% austenite plus 50% martensite. Answer will be 100% bainite, and this will be your cooling curve. So you're suddenly cooling up to 500, then holding it isothermally, then further cooling down. So here you'll find your bainite will be here. So here this is upper bainite, which will be coarser compared to your fine bainite, which will be forming below 400. Now in sixth question, you are cooling up to 450 degrees Celsius around here, and you are holding it only for 10 seconds. The resulting microstructure when the steel is cooled suddenly from 900 degrees Celsius to 450 degrees Celsius, held there for only 10 seconds, followed by sudden cooling to room temperature. So here your answer will be, your firstly bainite will form around 450 degrees Celsius, and also there will be martensite for remaining structure. So 50% bainite, 50% martensite. This will be your cooling curve. So initially you're cooling up to 450 degrees Celsius, then in 10 seconds you are going up to only 50% of bainite transformation. Then the remaining metastable austenite will convert into martensite when you are suddenly cooling it. So these are the steps on sudden cooling. First, at 450 degrees Celsius, your entire austenite is converting into metastable austenite. Then on holding it for 10 seconds, this metastable austenite transforms into 50% metastable austenite and 50% bainite. Then on sudden cooling, your 50% metastable austenite transforms into 50% martensite.
Ma'am, like suppose if we are doing a heat treatment
Yeah.
and we just touch the tip of that TTT curve. So in that particular case, like, will there be a fraction of perlite formed, or all martensite will be formed?
If you're just coming by touching this tip and you're directly cooling it, right?
Yeah, yes, sir, yes, sir.
Okay, so at the this is the starting temperature, so there won't be starting. It depends whether how percentage. If you are going inside this curve, only then there will be some starting of perlite formation. And mainly when you touch this graph, it is mainly around nose temperature, which is for bainite formation. Perlite, touching perlite and coming downwards is not possible in case of continuous cooling.
Okay, ma'am.
Okay. Next question is, you have to identify the correct statements. So these are related to annealing and normalizing. So first question is, Sanjeet, can you mute please? Sanjeet? By someone else. Why is there noise? Everyone is muted still. Okay, so in this question you have to identify the correct statement. So first is, annealing is used to relieve stresses and increase ductility, or normalized steel is harder than annealed steel, or annealing can be final heat treatment process for hypereutectoid steels, and the cementite plates are closer together in a normalized medium perlite compared to annealed steel. So your answer will be these three statements. This statement is incorrect in this case. In this case, annealing cannot be your final heat treatment in case of hypereutectoid steels, because there will be formation of a cementite network, which is not good for your mechanical properties of steel. And other statements are correct. So as in case of annealing, annealing's purpose is to originate a uniform and stable microstructure that most closely resembles the metal's phase diagram equilibrium microstructure, thus letting the metal attain relatively low levels of hardness, yield strength, and ultimate strength with high plasticity and toughness. And in case of normalizing, it is a technique used to provide uniformity in grain size and composition, and it will lead to formation of equiexed crystals throughout the alloy, and the term is often used for ferrous alloys that have been austenized and then cooled in the open air. It is used to refine the grains, decrease their average size, and produce a more uniform and desirable size distribution. Fine grained perlitic steels are tougher than the coarse grained ones. So your normalizing will give you tougher and fine perlitic structure. Eighth question is, you have to identify the correct statements. The crystal structure of martensite is hexagonal close packed, or the crystal structure of martensite is body centered tetragonal. The crystal structure of Fe3C cementite is orthorhombic, and transformation of austenite to martensite is a diffusional transformation. So first and last statements are incorrect. Your martensite is BCT type of structure. HCP is in case of epsilon carbide, and your transformation to austenite to martensite is a diffusional transformation. It is a non-diffusional transformation, a thermal type of transformation. And this is the structure of martensite, which is BCT type of structure. Here in octahedral voids, your carbon will be existing, and in this case a complex orthorhombic structure is in case of cementite structure. The cementite is your iron carbide, which is a compound of iron and carbon, more precisely an intermediate transition metal carbide with the formula Fe3C. By weight it is 6.67% carbon and 93.3% of iron, and it has orthorhombic crystal structure. It is hard, brittle material, normally classified as a ceramic in its pure form. In next question, in 8th question, you have to identify the correct statement. So first statement is the crystal structure. Okay, this one we have completed. Next one is medium carbon steel contains blank percent of carbon. So first option is 0 to 0.25, or second option is 0.25 to 0.55%, or 0.55% to 2%, or 2% to 4.3% of carbon. So in case of cast iron, as you know, for 2.14 to 4.3% your eutectic reaction will take place. So these are the cast irons, and the remaining three are low, medium and high carbon steels. So the classification will be based on carbon percentage. So up to 0.25% carbon, it will be your low carbon steels, and in between 0.25 to 0.55% carbon will be medium carbon steel, and above 0.55% it will be high carbon steels. Last question is, which impurities in steel causes hot shortness? Your options are FeS, iron sulfide, SiO2, silica, Al2O3, alumina, zinc oxide, ZnO. So your answer will be FeS. So when your steel consists some amount impurity of in form of sulfur, it will form FeS, which is a eutectic, and it will be having lower melting point, leading to hot shortness. So sulfur, which is generally in amount of 0.05% in steels, it combines with iron, forming iron sulfide. It in turn forms a low melting point eutectic alloy. This FeS phase is concentrated around grain boundaries, and your steel becomes brittle due to the melting of the iron sulfide, destroying the cohesion between the grains when forced or rolled at high temperatures. And in the presence of manganese, it forms manganese sulfide rather than iron sulfide, which passes out as a slag or remain as well distributed inclusion throughout the structure. Now we'll be going through some lecture notes. So first is the kinetics of phase transformation. So how your phase transformation, for example, from austenite to your perlite, or for example how your formation of any nuclei from liquid to solid transformation takes place. These things, they exist. So first is nucleation. So first there will be formation of some nuclei, solid nuclei in liquid form, or a nuclei in solid state of other phase. So firstly there will be nucleation, then there will be growth of that nuclei. In first case, nucleation can be of two types. First is homogeneous nucleation, second is heterogeneous nucleation. In case of homogeneous, your nucleation sites for the new phase form uniformly throughout the parent phase, and in second case, it is your heterogeneous nucleation, in which nucleation of new phase happens preferentially along certain geometric features such as crucible surface, inclusions, dislocations, and grain boundaries. So in this case, if you are, for example, you are pouring a liquid iron into some crucible, then the crucible walls will act as heterogeneity. So in that surface, your metal will more likely to get supercooled and will start forming nuclei. So these nuclei will then grow and form an entire liquid will get solidified. In case of homogeneous nucleation, there won't be such heterogeneities present, and there will be equal chance of formation of nuclei.
By heterogeneous nucleation mean more than one. Uh, uh, I mean oscillate and Fe3C. They are both nucleation is like that, or heterogeneous means more than one phase, isn't it?
No, yeah, heterogeneous mean there can be already existing some inclusions present which are in solid state.
So it doesn't mean there will be more than one phase.
No, there can be single phase as well. Like single phase is nucleating, but there is like already some inclusions present. For example, some silica particles are already present which are in solid state, and there are some the mold wall that will act as some act as different phase that is present there. So it will go and it will find some supercooling there, so it will go and nucleate there. So your whatever phase that is forming, that can be your single phase as well. It can be perlite as well, which is a phase mixture.
Ma'am, by meaning the crucible surface means.
Crucible surface, crucible meaning your mold, like in which you are pouring your hot metal. It can be a crucible meaning a refractory lining. Crucible meaning it's made of some silica or some ceramics which is used for hot for pouring of hot metal.
Okay, ma'am.
Okay. Now in case of homogeneous nucleation, it refers to the formation of nuclei of new phase uniformly throughout the parent phase. Here we refer to phase transformation from liquid state to solid state, or phase transformation within a solid phase. Now phase transformation depends on the important thermodynamic property, which is change in free energy, delta G. Now this transformation occurs when there is reduction in free energy, delta G less than 0. Now here the nuclei that are forming are have the same probability across the entire volume. Homogeneous nucleation in case of solidification of a pure metal. Now in this case we assume that the nuclei of solid phase form within the interior of the liquid, and we assume that the nucleus is in spherical shape with a radius of r, which is shown here. So this nucleus will have certain surface and a volume. Volume will be 4 by 3 pi r cube, which is a sphere's volume, and 4 pi r square will be its area. Now there are two contributions for the free energy change. Now free energy difference between solid and liquid phase volume free energy. that difference will be your driving force. It will be helping for the formation of this spherical, while uh, other is your surface energy, which will be preventing the formation of sphere and its growth. Now here delta GV is always negative below freezing temperature, and the contribution from solid liquid phase boundary during the transformation of surface energy gamma, and the total free energy change will be volume free energy plus surface energy. In this case delta GV will be is in per unit volume, so you have to multiply your volume of the sphere, and your per unit surface area is your surface energy, so you have to multiply it with the surface area. And this is how with increasing radius of this nucleus your energy will change. So surface energy is positive, which will be preventing the formation of this nucleus, and your driving force is your volume energy, so this will be negative, so it is keep on increasing in negative. So the addition of both of these will be this total energy, which is this curve. So this will achieve maxima at certain point, which is known as your activation energy, and per, respective to this radius is called critical radius. The critical radius, below this radius your nuclei, this nuclei will be called embryo, and above this it will be called a stable nucleus. So the total free energy change increases, passes through the maximum and then decreases. The trend of delta G physically implies that the free energy increases as a solid particle starts to form through the clustering of the atoms in the liquid. If the cluster size reaches a critical radius r star, it will continue to grow as the free energy starts decreasing thereafter. If the cluster radius is less than r star, it will shrink or dissolve in the liquid, and the subcritical particle with radius less than r star is called an embryo, and the particle with radius greater than r star is called nucleus. The free energy change at critical radius r star is called critical free energy change delta G star, which is called activation free energy. Now the free energy required for the formation of stable nucleus is the activation free energy, and delta G star is the energy barrier for the nucleation. Now will be initially when we got this delta G, now delta G upon dr, you'll be getting 4 by 3 pi r cube plus delta times delta GV plus 4 pi r square gamma. Now after differentiating it with respect to r, you'll be getting 4 pi r square delta GV plus 8 pi r gamma, when you'll be keeping it equals to 0, where your this r star will be critical, so you can get r star value to be minus 2 gamma upon delta GV, and your when you put this value of r star in your initial equation, this equation, you'll be getting delta G star, which will be 16 pi gamma cube divided by 3 delta GV square. And the driving force for the solidification is the volume free energy change, and this delta GV in terms of your change in enthalpy, it can be written as delta HF times Tm minus T. T is your temperature up to which you are cooling, so delta T is your supercooling that you are provided, divided by Tm, melting temperature. Now
Ma'am, why that volume energy is taken as negative? free energy for volume is taken as negative in the first graph.
Free and which one? Your
Uh,
volume?
Volume free energy is taken as negative and
Yeah.
surface free energy is taken as positive.
Yeah,
Why?
so when you think about the formation of a nucleus, then volume energy is what that is coming because of formation of a stable nucleus, stable, structure. In that case, there'll be formation of bonds. So as the bonds are forming, the energy will release. So because of the release, there'll be negative in case of your volume energy. Surface energy will be because of the solid liquid interface is present there. So because of that boundary that is present, because of that there is requirement of the energy to keep this stable. So this part is positive. So you have to continuously work against this energy while the formation of a solid state that is providing you some energy. So that is in terms of negative release, and that is energy release.
Okay, actually, the volume energy will be working against the surface tension force.
Yeah, both are trying to balance, and when they are balancing, that is where you are getting your critical nucleus.
Okay, ma'am.
Now the effect of temperature. So as you keep on increasing your supercooling, and then you'll be getting your change in this curve. So this curve will be lower compared to this curve, so there will be less activation energy required if you are providing higher supercooling, and the size of critical radius will also be lesser. So your solid will be having more number of nucleus because the size required is lesser. So your fine structure will be forming when you are providing higher supercooling. Now, comparison between homogeneous and heterogeneous nucleation. So in case of heterogeneous nucleation, it refers to nucleation starting on pre-existing surface and interfaces. Now this is your interface that is already present, and on this your liquid is solidifying. Now nucleation on flat surface, there are three interface surface energies. Solid liquid interface energy, so SL is your this energy which is in this direction, and by taking cos theta you are taking it in this direction. These two should balance, this gamma IL. So gamma IL will be equals to gamma SI plus gamma SL cos theta. Now the activation free energy will be lesser than in case of homogeneous nucleation, where R star remains the same. So hence heterogeneous nucleation occurs readily and at an undercooling of few degrees Celsius rather than few hundred of degrees Celsius in case of homogeneous nucleation. So you have to just provide up to few degrees of supercooling in case of heterogeneous nucleation. And the undercooling for heterogeneous nucleation is less than the homogeneous nucleation, and maximum nucleation rate for heterogeneous nucleation occurs at higher temperature than homogeneous nucleation.
Ma'am, by meaning the supercooling, are we meaning is cooled in higher, faster rate? And
Supercooling is your delta T that you are providing. So in this case, okay, like here at this temperature from austenite to here in that other, one second, in which, in equilibrium diagram, okay, from here to here, when you are coming from this transformation line, your austenite won't directly change to gamma plus Fe3C, right? You have to provide at this temperature, you won't be getting transformation, you have to provide certain undercooling. When you cool down to this line, only then there will be formation of some nucleus. So that undercooling, that is your delta T, from equilibrium temperature minus the temperature that you are taking. That is your delta T. So that you have to provide to start your transformation.
Ma'am, that means that undercooling and by meaning supercooling, is it related to that transformation diagram?
Yes, like there'll be, you require certain energy for beginning of the formation of these nucleus. So it won't start at that exact equilibrium temperature when you are cooling down. You have to provide certain undercooling for formation of these nucleus. In ice,
Okay.
okay. Okay, after this, the growth of an embryo. So if we saw nucleation, two types of nucleation, then after this there is growth of an embryo. If someone's mic is on, because there is a noise in background constantly. Everyone's mic is also on mute. Okay, in case of growth, so the growth begins when the embryo reaches a critical radius. So after it has reached this R star, after R star, after addition of each atom, that is called growth. So nucleation continues elsewhere in the liquid phase, and your growth process ends when the particle of new phase meet at in any region. So when this particle meets other particles, so then your area is restricted, so in that case your growth will stop. The particle growth happens through long range atomic diffusion in stages. So there will be first diffusion through parent phase, then diffusion through phase boundary, then diffusion into nucleus. And your growth rate can be described like the rate of diffusion, and the rate of transformation and the time required to complete the transformation to a certain degree are inversely proportional. So these two graphs are almost mirror to each other, because the if you have higher rate of transformation, then you'll be getting in less time you'll be getting your material transferred. And for example, the time required to complete 50% of transformation is represented as T.5 at different temperatures below solidification temperature. That shows a minimum that corresponds to the maximum of overall transformation rate. So at the point where your rate of transformation is highest, you'll be requiring least time for the complete transformation of your phase. Now the size of the product phase particles depends on transformation temperature. So if you are moving very low in below the melting temperature, so if you are providing very high undercooling, in that case your growth will be keep on reducing. So growth will be highest near high temperature because it is diffusion based. So diffusion will keep on reducing as you keep on going down. Now transformation taking place close to Tm has low nucleation rate but higher diffusion rate. Hence few nuclei will grow over large size, leading to a coarse grain microstructure. And your transformation at low temperatures will be corresponding to high nucleation rate because critical size will be reduced, and the low growth rate. Growth will be because it is diffusion based. Hence microstructure will be of fine particles. And if the material is cooled rapidly in the transformation temperature range, the situation corresponds to very low transformation rates, which will possibly producing non-equilibrium phases. Now this is how your overall transformation will take place. So growth will be keep on reducing while nucleation attains some maxima at certain supercooling, undercooling, and the addition of both of these rates, it will give you overall transformation rate. So if you are in this region at this undercooling, you will be getting moderate transformation, and here you will be getting highest transformation at this particular uh, undercooling, and below this temperature you will again be restricted because of the your growth rate, and in above region you will be restricted because of nucleation rate. Now
By
classification.
meaning highest transformation means more nucleation.
Can you repeat?
By meaning highest higher transformation rate means more nucleation.
No, transformation is addition of growth rate and nucleation rate. So if there is highest transformation rate, then in that case your growth rate is also high, meaning it will be the addition of both of these will be highest, because highest nucleation rate you are getting here at this point, but at this point your growth rate is very low, so addition of both of these will be highest around here. You'll be getting high
Okay.
growth rate as well as high nucleation rate.
So which one is more desirable? Actually, when the growth rate is increasing, then we will be getting larger microstructures in it. So it will be weaker.
Yes, so it depends on what type of structure you want, right? If you want coarser structure, then you'll be providing less supercooling. If you want uh, finer, then you'll be providing high cool undercooling. If growth rate is high, transformation rate high, meaning you'll be completing your entire transformation very fast, like up to 10 second you'll be getting your entire material transformed. But if you are only finding out that your desirable microstructure is fine structure, then you won't be wanting that my transformation completes in very less time. It depends on what type of properties you require.
Okay. Okay.
Okay. Now moving on to steels. So in case first, steels are classified based on methods of manufacturing. So for example, they can be made into Bessemer, then in that case it will be Bessemer steel, open hearth steel, based if it's made into open hearth, electric furnace steel, or crucible steel. And based on uses, it can be machine steel, which will be used for making machines, spring steel, which will be used for springs. In this case your steel will be having high percentage of silicon, boiler steel, structural steel for making structures, tool steel, which will be high in carbon and in various alloying elements. Based on chemical composition also, it can be either based on carbon percentage or based on alloying elements, and this is most popular classification. So in case of carbon content, it can be low carbon steel, medium carbon steel, or high carbon steel, and in all these steels certain amount of manganese is present to improve hardenability. Now SAE steel grades by chemical composition. So these steels are designed by designated by 4 or 5 digit number system, which represents the approximate content of the important alloying elements. So your first digit, if it is 1, then it will be carbon steel. For 2 it will be nickel steel. For example 3 it will be nickel chromium. molybdenum steel for 4 in this manner. And for alloy steel, second digit indicates the approximate percentage of predominant alloying element, and last 2 or 3 digits indicate the mean carbon content divided by 100. For example, 2520. In this case, 2 will be indicative of what type of steel is there. So 2 will be nickel steel. 5 will be percentage of nickel. So there will be 5% of nickel, and 20. So you have to divide 20 by 100. So it will be 0.2% of carbon in this steel. In addition to the number, AISI specification may also include a letter prefix to indicate manufacturing process employed in producing steel. Now, effect of some alloying elements. First is sulfur. In case of sulfur, which is 0.05%, it combines with iron, forms iron sulfide, as I told earlier during telling question. So this FeS, it forms low melting point eutectic alloy, and this FeS phase is concentrated around grain boundaries, and this steel becomes brittle due to the melting of iron sulfide, destroying the cohesion between the grains when forged or rolled at high temperatures. And in the presence of manganese, it forms manganese sulfide rather than iron sulfide, which pass out as slag, or it remains well distributed inclusion throughout the structure. And for free machining steel, sulfur is added up to 0.08 to 0.35%, which improves the machinability due to presence of a greater number of sulfur inclusions, leading to breakup of chips. Other element is silicon. Silicon content in commercial steels is in the range of 0.05 to 0.3%, and the silicon dissolves in ferrite, increases the strength of the steel greatly while decreasing the ductility. It promotes the deoxidation of molten steel through the formation of silica, thus leading to the sound castings. Then manganese. It is present in all commercial plain carbon steels in the range of 0.03 to 1%. Manganese counters the ill effects of sulfur by forming manganese sulfide. If more manganese is present, then it forms a compound with carbon as Mn3C associated with cementite. And it also acts as a deoxidizing agent, improving the soundness of castings, and steel is called an alloy steel if manganese content is higher than 0.8%. Another is phosphorus, which is generally kept below 0.04%. This small quantity tends to dissolve in ferrite, increasing the strength and hardness slightly. In some steels, 0.07 to 0.12% phosphorus seems to improve cutting properties, and in large quantities, this phosphorus reduces ductility, leading to cracking of steel when cold worked, making it cold short. So your sulfur will be responsible for hot shortness, and your phosphorus will be responsible for cold shortness.
Ma'am, can you explain that hot shortness and cold shortness?
Okay, so hot shortness will be when you can't heat your material. You're restricted by some temperature because it is forming FeS, right? FeS will be having low melting temperature. So you can't, if you roll it at higher temperature, then it will be restricting your steel. So that will be your hot shortness when there is certain amount of sulfur present. Cold shortness will be when you are at lower temperatures. If there is high amount of phosphorus present, your material will become brittle. So it will lead to cracking of steel. So it is your restricted by uh, your lower temperatures, your steel. You can't use it in lower temperatures. It also changes your yeah.
I mean, in the hot shortness, actually, it will be resisting the rolling. During rolling, it will be resisting it due to the presence of sulfur.
No, there's if it yeah, in case of rolling at high temperatures, your this FES it is formed, then it is going at grain boundaries, right? Then it is your steel becomes brittle due to melting of iron sulfide. It is melting at even lower temperatures, such as around 700. It will be melting this your, and this is at grain boundaries, so your material won't be having good properties.
Okay, ma'am. Actually, these small amount of these elements will be around the grain boundaries. I mean that we add manganese, chromium like that. They'll be forming around the grain boundaries.
Manganese you are adding to prevent formation of FeS. If MnS is forming, it is better for your steel, because if MnS is forming, then it can be either removed by slag, or it will be in form of inclusion, then it is better. While FeS, when it is forming, then it is going at grain boundaries.
Ma'am, by meaning the inclusion, it's actually during that tensile test, if there is any inclusion in the material, then it will be starting leading to the crack formation, isn't it?
Yes,
So
yes.
why we are saying that MNS will be good.
No, MNS will be good compared to your when it is present in form of FES. If FES is present, you can't hot roll your material. Compared to FES formation, MNS is better. It's not very good, but it is better compared to that. It will be well distributed, then it will be like a dispersion type of hardening will be there.
Okay, ma'am. In both the hot shot and cold shot, the result will be like the material will be become more brittle.
Yeah.
Okay, ma'am.
Okay. Now austenite transformation. Now, in case of iron carbide equilibrium diagram, we see that they may not be used to study steels cooled under non-equilibrium conditions. So, in case of equilibrium only, you'll be finding the pearlite formation, or the phases that are told in case of equilibrium diagram. Austenite is not stable below lower critical temperature 760 degrees Celsius. Hence, it is important to know that how long does it take for austenite to transform at a given subcritical temperature. Also, it is important to know the details of the transformation products obtainable after such transformation. So, in case of annealing, normalizing and hardening, these are three heat treatments that we'll be talking after some time. So in this case you'll be getting different phases than pearlite. In case of isothermal transformation diagram, so this is the how you can form these diagrams. So for this, the austenite transformation may be understood through isothermal transformation diagram. And how to produce such diagram? In step 1, you have to prepare several samples which are cut from the same bar. It should have same composition. And we place these samples in a furnace or molten salt bath at the proper austenizing temperature for long time for transformation to complete austenite. Now it has complete austenite, and for example in case of 1080 steel it is 1425 degree Fahrenheit. And now step 3, you have to place the samples in a molten salt bath which is held at a constant subcritical temperature. It can be any temperature below A1. And after varying time intervals in the salt bath, each sample is quenched in cold water or iced brine. After cooling, each sample's hardness and microstructure are studied, and the above steps are repeated at different subcritical temperatures until sufficient points are determined to plot the curves on the diagram. These are the cooling curves. These are the curves which are with time at this particular, for example, at this point your percentage of perlite is 0, whole percent is austenite. Here is your transformation is started, and it will be in form of S curve, and it will reach 100 at this point. So in here to here it will be your transformation time. This is your incubation period up to which point your transformation is starting. Now the temperature plays an important role in the rate of austenite to perlite transformation. Your temperature dependence is shown in the figure in the form of S curve plotted with percentage transformation with respect to time. Time is taken in log scale, and for each curve your data were collected after rapidly cooling a specimen composed of 100% austenite to the temperature indicated and holding at that temperature throughout the reaction. So up to 100% cooling should meaning it is kept at 600 degrees Celsius up to this time, up to longer time, and after that it is quenched to room temperature. Now this is at 600 degrees Celsius, this is at 650 degrees Celsius, this is at 675 degrees Celsius. Like that you have to plot for all temperatures. Now these S curves, they are extended to make these triple T curves, isothermal transformation diagrams. Now more convenient way of showing the temperature dependence of this transformation is as shown on the bottom figure, this figure. And this vertical axis is temperature, horizontal axis is logarithmic of time. Red solid curve, it shows when your transformation will start, and the green solid curve, this it tells when your transformation will end, and dotted line is corresponding to 50% of transformation. These curves are generated from a series of experiments at different subcritical temperatures and then transferring data as shown for one temperature in the figure. Now this is at 675 degrees Celsius. So at this particular time, you know at what time your transformation is starting, at what time your transformation is ending. Like this you will be drawing multiple graphs and extending it to the triple T diagram. Now in this diagram is also called time temperature transformation diagram. Here horizontal eutectoid temperature line shows the stable austenite above the temperature, and austenite perlite transformation occurs only if the alloy is supercooled to below eutectoid temperature. The starting time and ending time of transformation depends on temperature. The start and finish line are almost parallel, and they approach eutectoid line almost asymptotically. To the left of the transformation start curve, only austenite is present. In this area you are having unstable austenite, and in the right of the transformation finish line only perlite is present. In between, the austenite is transforming to perlite, hence both the constituents will be present. The above diagram is only applicable for eutectoid plain carbon steel, and the diagram will change if we change the composition. So for the cooling curve, we are taking one particular cooling curve. So here up to the A, B, C, D, in the CD as it's shown with vertical lines, this is where your transformation is taking place. The cooling curve ABCD is superimposed on the IT diagram, and very rapid cooling of austenite to temperature is indicated by near vertical line AB. This AB is very sudden cooling. And isothermal treatment at this temperature, isothermal means at a single temperature. So holding of your material at a single temperature, it is your isothermal treatment at this temperature is indicated by BCT. Transformation of austenite to perlite begins as C, which is 3.5 second, and finishes at D, which is corresponds to 15 second. Now your thickness of ferrite and cementite layers in perlite, it depends on transformation temperature. So if you are transforming this, you are taking this temperature BCD line, if it is below this, then you will be getting finer perlite. At high temperature, carbon can diffuse long distances, hence it forms thick layers leading to coarse perlite. And at low temperatures, diffusion is less and hence fine perlite results. Now triple T diagram for eutectoid steel. Here only perlite will be present, there won't be any pro-eutectoid ferrite or pro-eutectoid cementite. So austenite transforms to another product called bainite, which is feathery structure at low temperature, while at high temperatures perlite forms. So higher temperatures than the this nose temperature up to 50, there will be formation of perlite, and below this there will be bainite up to M start temperature. Your austenite transforms to another phase called martensite at much lower temperatures, which is a needle-like structure. An austenite to martensite transformation is diffusionless, unlike austenite perlite and austenite bainite transformations. The martensite is non-equilibrium phase and hence does not appear in iron carbide equilibrium diagram. Formation of perlite and bainite. Now in case of perlite, first nucleus forms in form of Fe3C. So Fe3C needle will form initially, then in the adjacent areas there will be depletion of carbon leading to formation of alpha ferrite. So ferrite will form adjacent to this, then because of again there will be carbon rich area will form leading to again formation of these cementite needles. Now this type of nucleation and growth will take place leading to formation of perlite. In case of upper bainite, there is ferrite forms compared to in perlite where Fe3C forms initially. Now in the upper bainite, there will be formation of Fe3C needles surrounded to this Fe3C. These will be nucleated, then alpha will keep on growing and this type of structure will form. And in case of lower bainite, needle type of structure will form, while in this case plates will form. So in this case your epsilon carbide forms in case of lower bainite. So firstly ferrite is forming, then there is precipitation of epsilon carbide and this type of structure is forming. This is microstructure of upper bainite and lower bainite. In case of bainite, it forms as needles or plates depending on temperature. Bainite is composed of ferrite matrix and elongated particles of Fe3C. Your pearlite forms above the nose and bainite forms below the nose temperature. Pearlitic and bainite transformations are competitive. So if some portion of an alloy transforms to pearlite or bainite, transformation to other microstructure is not possible unless it is re-austenized, because these are stable phases. Now this is your pearlite formation and upper bainite and lower bainite formations. Other structure is ferrodite. So in this case, when you heat your bainitic or pearlitic structure, so spheroidite forms when pearlitic or bainitic steel is heated and held at temperature below eutectoid temperature for a sufficiently long time. For example, at 700 degrees Celsius for 18 to 27 hours. In this case, your Fe3C phase, it appears as spheres like particles embedded in continuous ferrite matrix. This transformation happens by additional carbon diffusion with no change in composition or relative amounts of ferrite and cementite phases. And this is what your structure looks like in your under microscope. This is your ferrite globules and this is your alpha matrix. This is a two-phase microstructure consisting of spheroidized carbide and ferrite, which is formed by heat treating pearlite, bainite or martensite at a temperature below the eutectoid temperature. Other structure is martensite, which is a BCT type of structure. Another transformation product like pearlite and bainite, it forms when austenized iron carbon alloy is rapidly cooled. Martensite is a non-equilibrium single phase structure. It is formed by diffusion less transformation, and in this case your FCC austenite converts into BCT type of martensite. This is what your micrograph looks like. In this case, it shows martensite microstructure having needle shaped martensitic phase, and white region it shows retained austenite because of rapid quenching. Now austenite, depending on cooling rate, so if you are slow cooling, then there will be formation of pearlite plus pro-eutectoid phase, and if you are moderately cooling, then it will convert into bainite. If you are rapid quenching, then it will convert into martensite. And the transformation is diffusionless and there is no change in chemical composition. Small volumes of austenite suddenly change its crystal structure, and the transformation proceeds only during cooling, and it ceases if cooling is interrupted. Hence, the transformation depends only on the decrease in temperature and is independent of time. And the transformation of the above type is called athermal, in contrast to one that will occur at a constant temperature with time. Martensite transformation, in this case the amount of martensite formed with a reduction in temperature is not linear, and the number of martensite needles produced at first is small, then the number increases and finally near the end it decreases again. And the temperature of the start of the martensite transformation is known as MS temperature, and that at the end of martensite formation is MF, martensite finish temperature. If the steel is held at any temperature below MS temperature, the transformation of martensite will stop and will not proceed again unless the temperature is dropped. And the martensite transformation of given alloy cannot be suppressed, nor can the ms temperature be changed by changing the cooling rate. ms temperature is a function of chemical composition only, so this ms temperature and mf, it will depend on chemical composition. And theoretically, austenite to martensite transformation is never complete, and small amounts of retained austenite will remain even at low temperatures, and the transformation of the last stresses of the austenite becomes very difficult at the amount of austenite decreases. Hence, MF temperature is clearly not defined for steels, as there is always some retained austenite. And this is how your amount of martensite changes with temperature in case of a thermal type of transformation. Some characteristics related to martensite microstructure. So first, it is hardest and most brittle microstructure obtainable in given steel. And your martensite hardness of the steel is a function of carbon content in the steel. So if there is higher amount of carbon, then hardness will be higher for martensite. And martensite results by cooling from austenite temperature rapidly by quenching before pearlite can form. And your quenched martensite structures are too brittle to be used, hence they should be tempered, because they'll be having residual stresses in them, and they will crack even upon if it's if it falls from certain height, it will be very brittle, so these should be tempered for their use. Reheating the as quenched martensite to a temperature just below the A1 results in best combination of strength and toughness for steels. Now, martensite transformation, martensite is never in a condition for real equilibrium, and although it persists indefinitely at room temperature, this is a metastable phase, and the structure may be considered as a transition between the unstable austenite phase and the stable mixture of ferrite and cementite. So if you heat your martensite at higher temperatures, certain higher temperatures, then it converts into ferrite and cementite, which are stable phases. Martensite is potentially very hard material, although it is harder than austenite. Extreme, extreme hardness is possible only with a sufficient carbon amount. High hardness of martensite is believed to be due to high lattice distortion. So as you are keep on increasing the amount of carbon, we see that around 0.8% we see the saturation in carbon. So after this, the hardness doesn't increase much, and it will be attain a saturation. So as you are increasing the carbon amount, your lattice distortion will be higher, and the formation of dislocations and twins, it will be higher because of high carbon amount which is going in your lattice of based in iron. Now, martensite transformation. The martensite transformation was firstly believed to be unique to steels only for many years. Then this type of this thermal type of transformation was observed in many other alloy systems such as iron nickel system, copper zinc system, copper aluminum system, and in case of shape memory alloys as well. This these also involve martensitic phase transformation. That's it for today. So if you have any query, you can ask.
By meaning the metastable state, it's not actually in equilibrium, but it will stay for more time.
Yeah, it will be it will be stable in those conditions. Like if you are rapidly cooling, then there's formation of retained austenite. So austenite is not stable phase at that particular temperature, but it is compared to what conditions it is subjected to. If you are not heating it at particular temperature, then it will be remaining in that state for very long time.
Ma'am, also the steel that we use is actually in ferrite form, or in mostly it is in the ferrite form.
The steels that we use.
Yeah. The temperature needs to be really. It will be using the steel in uh, normal temperature, isn't it? So actually, for the austenite and other delta ions, it will be higher than 700 degrees Celsius, isn't it? So we won't be for the structural works and everything. We will be using the temperature is very low. So at the low temperature, we are actually having only the ferrite or ferrite plus Fe3C. These two
Not
phases are actually.
Not necessarily. In plain carbons only you get ferrite phase. Like other steels are also possible. For example, if you add high amount of nickel and manganese, then they can make your different phases such as austenite. They are austenite stabilizers, manganese and nickel. So what they do? They reduce this your A3 line to very lower temperatures, and they make austenite stable at even room temperatures. So austenitic steel is also there. Martensitic type of steels are also there. Dual phase steels are also there. So it depends on what type of alloying elements that you are using. But in plain carbon steels, where only carbon is present, not alloying elements are not up to very high percentage, then it will be in form of ferrite and cementite. Yes.
Whether we use stainless steels of copper carbon content having more than 0.8% in stainless steel.
Yeah, in stainless steel, if you are using carbon content more than 0.8%.
Yes, that is like a hyper.
Yeah, in case of
Is that possible? Oh,
in case of certain stainless steels, carbon is seen as impurity. So in many steels, you keep it lower than 0.2%. So in some stainless steels, you can have high carbon percent as well. It depends on what properties you require. Like in case of tool steels, you require very high percentage of carbon because you want to form carbides, tungsten carbide or different molybdenum carbide. These help with you with cutting properties. So it depends
in order
on,
to have hardness. Mm.
yeah, so it depends on what properties you require.
In tool steel and die steels. Okay,
Yeah. Yes.
thank you.
Okay.
Madam, this is the last session,
No,
or
no.
one more
One more
session is there?
session. Yeah, one more session is there.
This recording we can get after the session is completed
Yes, you'll
in
be,
the
yeah,
site.
you'll be getting it on YouTube, and I think NPTEL will also be telling you the link of the recording, and the
Yeah,
slides will
in
also
the
be provided.
in this course. Okay.
Yeah, okay. If you have any query, you can ask, or you can leave if you don't have any query.
Well, by meaning the phase, actually, for the pure substance, the is the it only can have both three phases. I mean, vapor, liquid, or solid for the pure substance, and And also the heterogeneous phase means, for example, if alpha plus Fe3C is it actually heterogeneous phase?
Yes. Fe3C, it is a phase mixture. It is not a single phase when you talk about perlite. Single phase will be only iron or ferrite or Fe3C separately. Individually, these are single phase. If you are only seeing at Fe3C.
Ma'am,
The
but
parallel
we are,
mixture will consider as single phase.
No, perlite isn't a single phase. It is a phase mixture. Perlite is
Then,
also, benite is also a phase mixture.
but we can we'll treat it as one phase, or it is two phase,
It is a two phase. Like when you're
solid
talk,
plus solid.
yeah, it is having a phase boundary as well. Like Fe3C is there, alpha is there. These are two phases. It's not a single phase.
It's mixer,
Yeah,
like
phase.
how liquid and solid phase is there
Yeah,
in the same way. That means while applying this Gibbs phase rule to find the number of phases, so then in this phase, at this location, we have to take this perlite as 2.
I, for
Is it
that,
correct?
for Gibbs phase rule, I need to check whether you consider it two. Let me check.
Oh, yes, I got it out.
This point. Okay. Your freedom should be 0. Then you have two components. You have 1 degree of freedom. Austenite, perlite 3. Yeah, it will be 2.
2
Because
only, because
at this point you'll
ga,
be
ga,
getting, yeah.
yeah, gamma on cooling
Hmm.
it gives solid 1 plus solid 2,
Yeah,
that is cementite plus
ferrite.
ferrite.
Yeah,
It can be taken as 2.
yeah, it will be combined at the, for this point. You'll be, 1 second. Yeah, at this point you'll be getting three phases, right? Austenite, then cement, perlite will be your two phases. So three phases are there, components are two, and your degree of freedom to be 0, you'll be having to have three phases here. So cementite and ferrite you have to consider separately. Cementite and ferrite, yeah.
Okay, then in the case of hypoeutectoid steels,
Yeah,
actually it is proeutectoid ferrite plus perlite.
yeah.
Is it okay? Then that location, how many phases we have to take?
And proutec, you still have two because you are considering ferrite to be separate, right? In that case, proeutectoid ferrite is there, then they two are one phase.
Proeutectoid ferrite plus perlite.
Yeah. So in perlite, you are,
Perlite taking 2, as we
yeah,
are taking as 2.
yeah.
Then one more proeutectoid ferrite is there.
Yeah, perlite is same, right? In that case, you're getting proeutectoid ferrite and ferrite with perlitic ferrite. So those two should be same. You won't be having
Yeah,
three phases.
2 only.
Yeah, two only should be
Yeah.
there, I think. Because your austenite, here you have two, degree of freedom is 1 here. So
There is no such case of having 3 phases. Iron curve diagram or
three phases, Yeah, here austenite, ferrite, and cementite you had at eutectoid point. So it was three phases.
At that point only.
Yeah, at the invariant
Similarly,
points.
yeah, and even in eutectic point also it may be there.
Yeah,
Gamma
eutectic. Yeah, there as well.
eutectic. Okay, liquid
Gamma and
to
Fe3C, gamma Fe3C and liquid.
yeah. Even at peritic reaction also, you have three phases at that point, peritic point.
Yes, liquid,
Yeah,
then delta and your austenite.
austenite.
Ma'am, we will be having those phase boundary only if there is a, or in the case of Fe3 and carbon, alpha and Fe3, we are not having a phase boundary between them. I mean, if two boundaries, two phases are present, will there be a phase boundary between them?
Yes, if there are two phases, right? Phases will be separated by phase boundaries. Fe3C is there, then after that you have a layer of uh, ferrite. That is called your phase boundary between those. You're talking in terms of microstructure or here in phase diagram?
In both case, I mean, firstly, if we are talking about the phase diagram for the right side, we are having the two phase region alpha and F3C, isn't it? So in that region, will we be having any phase boundary? It's
In
a
which one?
heterogeneous space. In the heterogeneous space region, I mean, we'll be having more than two phases inside, or they'll be having like in that the perlite, we'll be having a lamellar-like structure, like one sheet of alpha and one sheet of Fe3C, like that.
In perlite, in case of your okay, this type of, I told it in previous case, right? Let me, yeah, in this case, right, here you're all, you have 100% perlite, but in case of hyper eutectoid steel, you'll be having some chunks of Fe3C. Your Fe3C will be either at grain boundaries, along grain boundary, or it can, if it is hypoeutectoid, then there will be chunks of alpha phase Fe3C chunks will be there. So at combined, you can tell there are two phases, alpha and Fe3C. So in case of perlite, there are already two phases and alpha will be counted as a phase. So which is you already counted in perlite.
Ma'am, here actually we are having two phases, but we are not drawing any equilibrium lines in between them. We are having some lines for austenate and separating the austenate and alpha and two phase region, isn't it? But in that two phase region, also we are having two phases. But why there is no boundary lines for them in the carbon iron carbon diagram?
Where I'm not getting what you're trying to say. Like separating what?
Like what makes us separate the alpha and the alpha
Inter-
ion?
interface you are asking, huh?
Yes, I mean we are having an interface of that uh, alpha and gamma and two phase regions, isn't it? What I'm asking is why there is no boundary lines for that two phase region.
Because there is single phase. In case, in terms of phase diagram, what you tell single phase region. So this is your gamma region. This is your mixture. So here it is your gamma plus some formation of some alpha. So alpha will form up to this point, then remaining your gamma changes into perlite. So below this line there will be formation of perlite. So this point corresponds to your eutectic reaction, this line. So where you are expecting to find boundaries?
I mean, we are for the mixture region. There won't be any these lines for the mixture region. If you take a mixture region of two
Mixture is not, see here gamma at this point your eutectoid reaction is taking place. So this, when you are cooling from this line, then your gamma is your gamma is transforming into alpha plus your Fe3C. So this reaction is corresponding to this cooling. If you are cooling at particular line, so this is temperature. So this I told earlier in previous lecture, right? So how you can convert your cooling curves into phase diagrams. It won't be telling you where the boundaries are. Like, it will tell you what phases are present in these various phase fields. These are phase fields. These are your corresponding to invariant lines. This is in invariant points. These are what told in phase diagrams. And depending
okay.
on phase diagram, you can tell what will be your phase structure. Like, you can tell if you are getting bainite martensite. That will depend on cooling rate.
Between two phases, actually, we have to treat that there must be some boundary when there are two phases. So the two phases are separated by a boundary. It's not that a separate boundary line will be drawn between the phases. Boundary will be there. That may be some kind of irregularity as far as the atom's orientation is concerned. Is it okay, madam?
Uh, I'm not getting the question actually. Like,
No, when
yeah,
adjacent to when adjacent to one phase, some other phase is present.
yeah.
Then to separate those two phases, there is no need to draw a boundary line between the two phases. We have to understand that a boundary is there because a phase difference is occurring at the interface. In interface, actually, it's a junction. Maybe that leads to a change of orientation of the atoms at the boundary.
It's like
It
compositional
cannot be
differences
represented
there.
by drawing a line.
Yeah, it's compositional difference. Like, if you're moving in particular direction, so there is Fe3C has different concentration of carbon, and alpha has different concentration of carbon. That's why it's like different phases that won't be in your phase diagram.
Yeah. Then to separate the two phases, no need to draw a line. I am asking. Just we should understand that whenever there is there are the number of phases are there between one phase and another phase. There will be a line. There will be a boundary. It's not line. There will be a boundary.
Okay, so in case of perlite, it is not a particular, it is a at a percentage level, right? It is fixed, like this percentage of Fe3C will be there, this percentage of alpha will be there. So that's what's showing in this region when you are forming perlite. It's a
Yeah.
constant. It's a constant line. For example, at 1.67%, you'll be having a single line for that percent carbide. So like that, you'll be getting some perlite which will be corresponding to only 0.8% of carbon, right? So if you move in this
Yeah.
direction,
Perlite means always it is obtained from the eutectoid composition.
composition, 0.8%
Yeah.
composition only.
Yeah.
So
Mm.
remain, if you move in this direction you'll be getting alpha, you move in this direction you'll be getting some Fe3C,
Fe3C, cementite.
proeutectoid, yeah. And when you keep on moving in this direction at 6.7% or so, you'll be getting Fe3C completely. So
Ah,
that will also be your, uh, there'll be composition will be fixed for that.
yeah. No, but whatever may be the projectile constituents, but for the perlite, always the amount of ferrite and cementite are
Cementite,
fixed.
yeah, their ratio is fixed, like how much,
Fixed.
yeah.
Yeah. Because you have alternate layers of so what is called the cementite and
Pearlite, yeah,
uh,
and alpha,
ferrite. Ferrite.
correct, yeah.
Uh, so, but in the case of normalized steel,
Yeah,
these layers are thin, and whereas in annealing, these layers are some a little bit. The width of the layer will be more.
will be more, yeah. In case of normalizing, there will be one more point as well, like in normalizing you are cooling with air cooling, so that won't be an completely equilibrium structure. So there can be
Yeah.
higher concentration of carbon that can be accommodated into perlite. So you can have fully perlitic structure but having higher percentage of carbon, more than 0.8%, because you are cooling non-equilibriumly.
Yes. Yes.
Yeah,
So we cannot compare it with the iron carbide diagram.
yeah, because it is equilibrium
It's
diagram.
non-equilibrium.
Yeah, iron.
Non-equilibrium.
Yeah,
Yes. Yeah. Yeah. Non-equilibrium. Actually, there are different situations: equilibrium, non-equilibrium, athermal. Athermal means only in the formation of martensite only we get that situation.
yeah, in martensitic type of, yeah. Then you'll be heat. You'll be changing the temperature delta T only, then you'll be getting some change in structure. You want, if with time you won't be changing, seeing any change in structure, that is a thermal.
Change in
It
structure means
depends on, yeah,
if we suddenly
temperature
stop
dependent,
cooling.
yeah. In between ms and mf, if you if you
Suddenly
stop cooling
stop.
bit, so if you're cooling only up to m 50% and you are just stop it, with time it won't change the percent fraction of martensite, it won't change.
Okay, then the remaining austenite will be like retained austenite or
Retained austenite, yeah.
okay. Thank you.
Okay.
Ma'am, in the case of that Hume-Rodri rule, if the free energy is higher, then if we substitute the solute atoms, they won't be in a stable state and they will decompose. Is it like that? If the free energy is higher,
Energy should reduce, right, for structure to be stable.
so does that mean if we try to substitute the solute atom, they won't be get into a stable phase. Instead, they will be decomposing.
Yeah, so Hume-Rothery rules has four rules, right? So if the change in difference in atomic size is higher, and if there is more electronegativity, so those things will define whether the entire energy is reducing or whether it's becoming higher. So it will depend on that. It should be like, it shouldn't change your structure much. If you are like in case of nickel matrix, you are changing it with copper atoms, then there will be completely substitutional solution, complete solid solubility.
Ma'am, in the case of the eutectic alloys, why we are getting that lower temperature than the alloying metals? For
Sorry,
the
in case of,
eutectic alloys,
yeah, why we are getting?
lower temperature than the alloying elements. Like we are actually adding the if the A has a higher melting point and B has a lower melting point than the A, when we are increasing the composition from when we view it from the right side, actually we are adding A to the B. So for that part, why the melting point is reducing? Actually, we can justify for the left part. There is a diagram for the previous lecture, isn't it? Like if for the utility alloy system, the melting point will be lower than A and B.
Okay, why it has a particular composition at which your eutectic alloys form. So it is kind of characteristic of eutectic compositions that will be having like lowest temperature. I don't know the exact reason behind it, but like at an exact composition you'll be having the lowest temperature possible for the entire phase diagram, which is used in case of your cast iron and in solders.
Okay.
Anything else?
Ma'am, in that eutectic system, actually, there was a point like for the pure metal, we will be having a constant horizontal line, and for the when we are alloying, it will be it won't be like that.
Which line?
For the eutectic phase diagram, there was a cooling curve for the phase diagram. So there was a point like pure metal shows a horizontal line as phase transformation happens in constant temperature,
Yeah,
but we are having a T1 and T2 for the uh, other one. For the solidification.
because there are two separate entities, right? There's two separate alloys present. So one will have different freezing temperature, another one will have different freezing temperature, A and B. You are forming two phases, right? Alpha plus beta. So it isn't like entirely, in case of pure, you have only A type of atoms. So they are combining and forming after particular undercooling. You are forming it at a constant temperature.
So that's the reason that we are getting a liquidous line like that.
Liquidus line, liquidus line is because of the cooling curves. At eutectic composition, you will be getting A1, A2. That's what you are asking.
Actually, for the there was a diagram like temperature time diagram, and there was a temperature combustion diagram. In that temperature time diagram, it was written T1 and T2 with a different slope, with a slope, and but in temperature combustion diagram, the same T1 and T2 is shown as a straight line.
Okay, let me check. Eutectic ones. will be getting different temperatures, like their alpha is forming in particular temperature range. So if you are in hypoeutectic region, then alpha is forming, then eutectic mixture is forming at a single temperature. So that's what will be happening. Mixture has a single point, single melting point, like pure elements. So that's what is corresponding to.
Okay. Thank you, ma'am.
Okay.